Alright everyone, so welcome back. Today we are going to continue on talking about another application for derivatives. And this is what's going to be called related rates problems. So the idea with related rates problems is that you have at least two quantities, maybe more. For the most part we'll just stick to two, maybe three. And these quantities are all related by some equations. And what we'd want to see is we want to see how changes in one or maybe more of them result in changes in a particular one of our quantities. And we'll see what we mean with some examples. So the simplest usual ones are areas and dimensions. So for example, suppose that we have a penny that we're going to drop into a pond, and the ripple's going to start spreading outwards in a circular ring from the center. And what we're going to see is if the radius is growing at a rate of 30 centimeters per minute, we want to see how fast the area of the circle is growing. Okay, so the setup looks something like this. So we have a circular ring, and we have some radius to that circle. So we'll call our radius r, and we'll say that our area is a. Well, we know that the area of a circle is given by pi r squared, and what we'll assume here is that both of our functions are functions, or both of our quantities are functions of time. So the radius increases with time, and that means the area increases with time. We don't know anything about how these functions are increasing with time. We don't know how the area or how the radius increases with time. It could be linear, it could be quadratic, it could be something else entirely. It's a mystery function with respect to time. So at no point are we going to try and find it. At no point should you ever try and find it, because it doesn't really matter for what we're going to try and do. Okay, and then what we said is we want to find how the area is increasing with time. Well, we're given that we have this relation a of t is equal to pi r of t squared. We're given what dr by dt is at a particular radius, and because we're looking to see how area is changing with time, that suggests we should be taking derivatives of both sides with respect to time. So we'll do implicit derivatives. So we'll take our derivative on the left-hand side, get dA by dt, and then on the right-hand side we'll have a chain rule. So we have the derivative of r of t squared with respect to t. From our chain rule, we'd know that that would give us 2r of t times dr by dt, with that pi out in front because it's a constant. So on the right-hand side, we'll get 2 pi r dr by dt, and then at this point, we just want to go and plug in all of the things that we're given. So we know that at the radius of 50 centimeters, that our radius is changing at a rate of 30 centimeters per minute, and that tells us that the area is changing at a rate of 3,000 pi centimeters squared per minute. So one other thing that you can do to kind of keep track of whether or not you've probably got to the right place is you can look at the units. So in this case, our units are centimeters squared per minute. So we have a length squared by time. And we're looking for how an area is changing with time. Well, units of area are always going to be length squared. And changing an area with time should give you units of length squared divided by time unit. And that's what we have here. We have centimeters squared per minute. Okay, for another example, we want to see how fast the area of a rectangle is changing if one side is 10 centimeters long and increasing at a rate of 2 centimeters per second, and our other one is 8 centimeters long, decreasing at a rate of 3 centimeters per second. Well, so what we'll do here is we'll start out by saying the area of our rectangle is given by the width times the length. And then we'll assume that both our length and our width are functions of time and changing. So we'll have that a of t is equal to w of t times L of t. And then again, we want to go and take the derivative of both sides with respect to t. Well, we have the width times the length, so we have two functions of t multiplied together, and that says that we should be using the product rule. So we'll get that dA by dt is going to be w prime times L plus w times L prime. And then from there, we're going to want to go and plug in the various things that we're given. So we're told that so that w prime is 8 centimeters and decreasing at a rate of 3 centimeters per second. and L we'll say is 10 centimeters long, increasing at a rate of 2 centimeters per second. And from there, we get minus 3 centimeters per second times 10 centimeters, plus 8 centimeters times 2 centimeters per second. And we put that together and we get minus 14 centimeters squared per second. And again, we're looking for a change in area with time, so we get units that are length squared divided by time, which is exactly what we'd want. One other thing to keep in mind with units is that you can only add or subtract quantities together that have the same units. So in this case, we have units of centimeters squared per second on both terms, and that's good. We can add them together. So if you ever run into situations where your units don't make sense, that's a very good indicator that you've done something wrong. You just want to go back and make sure that everything works. Figure out where you've made an error. Okay, so I've organized how we're going to solve these problems into 7 simple steps, and I want you to use these for solving homeworks, worksheets, tests, mostly because it helps you organize your work, and it also really makes it easy for me when I'm looking at it. Okay, so the first thing you want to do is you just want to read the problem very carefully, figure out what you're given, and also what you're going to try and find. The next thing that you might want to do, depending on the problem, is you want to make a sketch. So that can kind of help you to organize everything, maybe see what the relationships are. The third thing you want to do is go and define any symbols or variables that you're going to use. So if we come back to these examples, we're here defining the area, the width, and the side length. If you just start putting down variables here, it's maybe not clear what they mean. And for some of the problems that we're going to do, it's really important to go and actually to know what the variables are describing, because if you're not paying attention to what the variables are describing, it'll lead you to the wrong solution. Okay, so then the fourth thing that you want to do is come up with important equations. So these are going to be relations that will tie everything together and help you solve the problem ideally. The fifth thing that we want to do is take the important equations that we have and differentiate everything with respect to time. From there, we'll go and substitute in all of our givens and then solve. And then the last thing we'll do, because this is usually good form, is to just go and make a concluding statement that answers the original question asked. So here, for example, we were asked to find how fast the area is increasing, and we could just conclude this with a simple sentence that says the area is decreasing at a rate of 14 centimeters squared per second. Okay, so we'll work through 3 examples of these, and then I'll have a worksheet over a couple more for you to work on. Okay, so the first one that we have is an aircraft is flying horizontally at a speed of 600 kilometers per hour, and what we want to see is how fast is the distance between the aircraft and a radio beacon increasing a minute after the aircraft passes 5 kilometers directly above the beacon. Okay, so let's see what we have in this picture to try and set things up. So we have this radio beacon here, B, and 5 kilometers above it, we have an airplane that is going 600 kilometers an hour horizontally. So this variable x is going to give us the horizontal distance between the radio beacon and the airplane. The 5 kilometers is giving us the height at which the airplane is flying, and this red dashed line y is going to give us the distance between the airplane and the radio beacon. So what we're looking to see here is how fast the distance between the aircraft and the beacon is increasing. So what we're looking to find in the end of this is dy by dt. Okay, so an equation that's going to be helpful in solving this problem is going to be the Pythagorean theorem. So we'll have x squared plus 5 kilometers squared equals y squared. One other very important thing to remember in these kind of problems is that whenever you're given a constant, you can put that in at the beginning. But if you're given a value that is changing, so such as the side length x, and you're given what's happening at a particular point in time, you cannot just put that in at the beginning. You have to put that in at the very end. So if you're unsure about what you can put in at the beginning or not. It's probably simpler just to define everything as a variable and note that the change with respect to time of anything that's constant, so in this case the 5 kilometers an hour, that change would be 0 because it's a constant. Okay, so then step, well I guess 5, we want to differentiate the equation that we have in step 4 with respect to time. Okay, so the equation that we have is our Pythagorean theorem, x squared plus 5 kilometers squared equals y squared. And when we differentiate that with time from our chain rule, we'll get 2x x prime of t equals 2y y prime of t. And now we want to solve our equation for y prime, so we'll get that y prime is going to be x times x prime all divided by y. From that, we just want to go and plug in the givens that we have. So from this, we're told that x prime, so that horizontal distance between the radio beacon and the airplane, is increasing at a rate of 600 kilometers an hour. So our x prime will be 600 kilometers. We just need to come up with what x and y will be. Well, we know from our Pythagorean theorem that x squared plus 5 kilometers squared equals y squared. And we're looking at what's going on 1 minute after the aircraft has passed the beacon. So we'll just see the distance that the aircraft is away from the beacon horizontally 1 minute after passing it. And when we do that, we'd see, well, if it's going at 600 kilometers an hour, it's going at 10 kilometers per minute. So we'd get that our distance x at the point we're concerned with is going to be 10 kilometers. And then we'll put that into our Pythagorean theorem to get our relationship for y. And when we go and we simplify everything, we'd see that the distance is increasing at about a rate of 537 kilometers per hour. So we could just give a concluding sentence that we have there. So just the distance between the aircraft and the beacon is increasing at a rate of 537 kilometers per hour, and that would be a good final answer. Okay, for our second problem, we're going to have a lighthouse L located on a small island 2 kilometers from the nearest point A on a long straight shoreline. And we're told that the lighthouse lamp is going to rotate at a rate of 3 revolutions per minute, and what we'd like to find is how fast the point P, which is where the light beam is hitting the shoreline, is moving along the shoreline when that point is 4 kilometers from this point A. So as in the last one, we've got a triangle, and what we're going to want to do is just go and label a couple of sides here. So one thing that we see in this triangle is that the lighthouse is going to be 2 kilometers away from the shoreline A, so we can go and put that in, and we'll treat it as a fixed constant because our lighthouse isn't going to change sides. And then we're going to have this side length y, which is going to give us the distance between A and P, and then we'll also have the other side in this triangle x, which we'll just kind of leave alone for the moment. Okay, so from this, what we're trying to find is how fast the illuminated spot P is moving along the shoreline. So in other words, how fast is the distance between A and P increasing? So we're going to be looking for dy by dt again. One thing to keep in mind in the way that we've got the diagram set up is none of these pieces that we have in here are going to have anything to do with this rotation of 3 revolutions per minute. So what we should do is we should go and also put in a variable that's going to tell us, going to make this 3 revolutions per minute matter. So what we could do is we can bring in this angle theta, which is going to give us the angle between the light beam and the shoreline. So what this is going to say is that d theta by dt is going to be 3 revolutions per minute. So that's going to be the rate at which the lighthouse, the lamp is spinning around the lighthouse. Okay, so one temptation that we may have had is to go and use Pythagorean theorem to go and relate some of these things together. But if we use Pythagorean theorem, it's not going to invoke theta anywhere, and it's going to require having a derivative of x and also y of t. Well, we're trying to find y, so we don't know anything about that, and we also don't know anything about how x is changing. And if you ever put yourself into a position where you do something like this, you have 2 kilometers, an x, and a y, you're looking for how y is changing and you don't know how x is changing, that suggests that you should go and use a different equation. And when we have something like this, where we're told how an angle is changing, that says we should use a trig function in there somewhere. Okay, so we'll go and relate our theta, y, and 2 kilometers by tangent of theta. So tangent of theta is going to be y over 2 kilometers. Then we'll go and differentiate with time, so we'll say that theta and also y are functions in time and take their derivatives. So we know that the derivative of tangent is secant squared. So on the left-hand side, based on our chain rule, we'll get secant squared secant squared of theta times d theta by dt. And on the right-hand side, we just have 1 over 2 kilometers times the derivative of y, so we just get 1 over 2 kilometers dy by dt. Okay, now we want to solve things. So when we go and we isolate this expression for dy by dt, the thing we want to find, we'll get dy by dt is 2 kilometers times secant squared of theta times d theta by dt. And we just now need to figure out what secant squared is. So let's come back to the picture. And we'd said that we're looking for what's going on here when the distance between A and P is 4 kilometers. So y is 4 kilometers. Here's where we can use Pythagorean theorem to figure out the secant. Because the secant is hypotenuse over adjacent, so we need to figure out the side length x. From Pythagorean theorem, we'll get that x is going to be the square root of 2 kilometers squared plus 4 kilometers squared, or 4 plus 16, so square root of 20. And we could rewrite the square root of 20 as 2 times the square root of 5. So our secant will be 2 times square root of 5 divided by 2, or square root of 5, which is what we have right here. The other thing that we want to do is we always want to put things, put angles in terms of radians, so switch from revolutions over to radians by multiplying by 2 pi. So we'll get that d theta by dt is 6 pi radians per minute. And when we go and we combine everything together, we'll get 60 pi kilometers per minute. One thing to keep in mind here is that we dropped the radians unit. Radians are kind of a fictitious unit, which is, they're safe to drop. And again, we also get what we'd like, which is we're looking at a change in distance with time, and we get units that are a change in distance with time, so kilometers per minute. So we could say that the illuminated spot P is moving at a rate of 60 pi radians per minute. Okay, so the last problem that we're going to do is we're going to look at a leaky water tank that's going to be in the shape of an inverted circular cone. The cone's going to have a depth of 5 meters, top radius of 2 meters, and what we want to see is when the water in the tank is 4 meters deep, we're told that it's going to leak out at a rate of 1/12 cubic meters per minute, and we want to see how fast the water level is dropping in the tank at the time in question. And we're also given that the volume for a right circular cone is going to be 1/3 pi r squared times h. So whenever you're given a problem dealing with, I'll say, some non-standard kind of shape, so something that's not like a square, a rectangle, a triangle, a circle. Those ones I think everyone should be able to pull out off the top of their head. When you get something more obscure like a right circular cone, I'll give you any of the equations you need. So if you need a volume, I'll give you that. If you need a surface area, I'd give you that. But you should be able to come up with the area of a triangle or something. Okay, so we have that the volume is 1/3 pi r squared h. That's great. But what we see in here is that we have two variables. We have the radius and we also have the height. But we only have one equation, and we're going to need something else to go and simplify this down, because so far we have 3 unknowns and only one equation. We need to get a second equation to go and simplify things here. Well, so what we can do is we can take a look at this picture, and what we see is that we have similar triangles going on. So we have this, this big right triangle, we have a 90-degree angle, we have this angle down here, and then we have this third angle. But then in the triangle with the red dashed lines, we see we have a 90-degree angle. It has the same angle down here, and that means the third angle also has to be the same. So whenever you have similar triangles, the ratio of corresponding sides is equal. So we can take advantage of that to go and simplify our problem down from the variables r and h to just one of the two. Okay, so from the picture we could say that, well, we have this these two base legs, so we have that 2 divided by 5 is going to be r divided by h, so the ratio of corresponding sides is equal. In other words, what that says is that r is going to be equal to 2h over 5. So using this relationship that we have for r, or h, r in terms of h, we can put that into our volume expression and reduce it down to a volume just in terms of h. And when we simplify this thing down, we'll get 4 pi divided by 75 times h cubed. So that now is just a function for the volume in terms of a single variable h, and we can now proceed as we have in the last couple of examples. Okay, so we'll assume that everything is now a function of time and take derivatives with respect to time. So we'll take dv by dt on the left and get v prime. On the right-hand side, we have these constants, 4 pi divided by 75, which we can pull out in front, and then just take the derivative with respect to time of h cubed of time. So our height's changing with time, take implicit derivatives. From our chain rule, we'll get 3h squared times h prime. And the thing that we're trying to find in this expression is we're trying to find how fast the water level is dropping. So we're trying to find h prime here. So we want to isolate this expression here for h prime. So we want to isolate our expression for h prime, and when we do that, we get that h prime is going to be 25 divided by 4 pi times v prime over h squared. So we just want to plug in the givens that we have and then solve. So we're told that the water is leaking out at a rate of 1/12 cubic meter per minute. So in other words, the volume is decreasing as time increases. And when you have a quantity where it decreases as time increases, it's going to be negative. So in this case, dv by dt is negative. The water is going out. And we're looking at this when the tank is 4 meters deep, so our h of t will be 4 meters. And when we go and we simplify things down, we get minus 25 divided by 764 pi meters per minute. So again, what we have here is we have that h prime is negative, so it tells us that as time is increasing, the water level is dropping. That makes sense. That's exactly what we'd want. And in this case, what we'd see is that the height's actually decreasing at a pretty small rate. It's decreasing at about a rate of 1/100th of a meter per minute. And we also get the units that we would want, so we're dealing with just a length changing with time, so we get units of length divided by time. Okay, so those are a couple of examples of how you want to solve some related rates problems. There will be a worksheet sitting in WOW courses for you to go and do a couple more of these kind of problems. And I'll see you in the next video.